Hello, everybody. Welcome to second discussion in dynamics. Today we will be talking about projectile motion and uh, and 1D motion. Okay, so we're gonna do three examples. First two are projectile, basically, as you can see, and second one is 1D motion. Yeah, I believe we are able. I am able to finish three of them in 15 minutes. Yeah, let's see. Let's see if I can. And as a reminder, guys, really, please familiarize yourself with the problem statements before coming to our discussions. I believe that it's beneficial for both of us and for you especially, because why on earth you would like to spend your time on reading here? Yeah, let's maybe spend it on something more productive. Yes, like solving problems. Yeah, that's why I think that it's very beneficial for you to read it before. Yeah, and just maybe even start the solution or just basically to figure out what's going on there. Yeah, and again, don't use solution manuals while working on your homework. I think this is even more beneficial for you, yeah, because then you can basically exercise your brain, yeah, instead of looking at the solution without thinking. Okay, without further ado, let's do the example number one. Oh, or maybe there are some questions to what happened last time. Do you have any questions to what happened last time when it comes to material covered? Everything was fine? Yeah, everything is good. How about logistics? Have I forgotten about something when it comes to, like, I don't know, grade? No, grade, I don't care. Yeah. Logistics, fine. Anybody has any question? Example number one, then. Okay. So briefly, please familiarize yourself with the problem statement before we start our solution. Yeah. Okay, so what do we have in here? We have a particle, a point that starts its motion at point A, yeah, and it is basically, it has velocity v0, yeah, that is known. We are on Earth, so gravity is also known. We know the geometry, and they ask us to find this parameter, the distance d, okay? And we are going to find it. And by the way, you probably can see that I already introduced one more parameter, height, which is h, and based on this triangle, you can figure out that this is expression for h. Yeah. Okay. Solution. So this is how I solve those problems. Yeah. I just consider motion in the x direction. Separately from what's happening in the y direction, okay? So what happens in the x direction? Aha, we have our acceleration that is equal to 0, yeah? And it's not only 0, it is constant, yeah? And only if acceleration is constant, we can, but we don't have to integrate because we have ready to go formulas in our head, yeah, or on the cheat sheet, yeah. So velocity, only if acceleration is constant, is this v0x plus axt. Okay, and we already know that ax is 0. And let's find maybe v0x and v0y. So I believe I have to do these projections, right? So that would be v0x, this will be v0y, and I maybe can write them here. v0x is, I believe, for sure v0, and now sine or cosine? I believe cosine. Cosine alpha, and v0y has no other choice. It has to be sine. Okay, and also we can plug in numbers. Yeah, you can plug in values, and you can obtain that they are 2 for 1, 2 for 1 0.481 feet per second. And this guy is 64.705 feet per second. Great. So basically our Vx of t is also constant, yeah? This is basically V0x that is equal to 241.481 feet per second. Okay, this is our expression for velocity. But let's find also position, okay? So expression for position, and I'm going to say it one more time, only and only if acceleration is constant, okay? If acceleration is not constant, you must integrate, okay? But if it's not, we know it by heart, or it's on the cheat sheet. So it's x0 plus v0x t plus 1/2 ax t squared. So this is 0. Also this is also 0, yeah? Because our coordinate system is here, yeah? Our coordinate system is here. So basically x0 is also 0. Okay, so this is our expression for position. Okay, we're done with the x direction. Any questions to what happened? Yeah, I'm asking because the next steps right now are exactly the same in the y direction. So again, ay is equal to minus g, and what's actually more important is that this is constant. So again, we can use our formulas for velocity, for example. Very quickly. Yeah, this is our expression for velocity. Okay, and for position, it's analogical. T squared. Yeah. So this is 0 again for the same reason. This is minus g. So y of t is equal to v0 yt minus 1/2 gt squared. Okay, that's it. So, any questions? So how about somebody tell me? So I just would like to use these two equations, this equation and this equation. And can you guys tell me how to find this parameter, that parameter d? Because this is what they ask us. This is what they ask us for. Oh, sorry, I didn't see it.
X should be equal to d.
One more time?
X of t should be equal to d.
Okay.
And then we know that d is equal to, you rearrange our first equation up at the top, a to the
Okay.
and then you just plug that in.
Here. Yeah.
Yeah.
And exactly. Yeah. So I can plug d here. I have time, and basically I can plug time there as well. Yeah. Because exactly. Thank you so much. Thank you so much. And remind me your name. Thomas? Yeah. Okay. So I shouldn't have remind me, yeah, because you never said me your name earlier. Yes. No, sorry. Yeah. Okay. So basically, what Thomas said, point B. You know, so that point, guys, this red point here, yeah. Point B is reached at time, I don't know, time, let's say time t star. I will use t star, okay, t star, yeah. So basically, what Thomas said, he said that x of t star is d, and also y of the same time is minus h, yeah? Is basically minus d 10 of 10 degrees. This is what he said. Great. And we are going to follow his proposition. So we basically have d is equal to v0x of t star. And we also have that minus d 10 degrees is equal to v0y t star minus 1/2 g t star squared. Okay. I like when this is aligned, so I'm just gonna put it here. Okay, so basically we ended up with 2 equations and 2 unknowns. Yeah, because unknown is t star and unknown is d. Okay, so let's solve it. And I know, guys, that you know how to solve it. Yeah, you solve it like 300 times in your life or 255 or something. Yeah. So basically very quickly, okay? So from the first equation, we know that t star is, the other way around. D divided by v0x. Let's plug this one in the second equation. I believe that some of the d's can cancel out. Can be cancelled out, yeah, like that. And d is basically equal to 2v0 x squared divided by g. Okay, plug in values. Grab your calculators. I did it yesterday at home, and just to save your time, you should end up with d approximately 1609.143 feet. This is our answer. Okay, that's it, guys. Questions? Yeah. Last row, do you hear me well? Yes? You are not in the last row. Last row. Yeah. Fine? Yeah. I can volume up if you want. And how about font size once again? Font size is okay for you? Yeah. Okay, cool. Questions again? Yeah. Yeah. In my previous discussion, one person asked, how do I know that y0 is 0? Yeah, maybe in case some of you are wondering, because we start from 0, 0. Yes. So x0 is 0 and y0 is 0. Yes. Okay. Example number 2. Let's do it. Please familiarize yourself with the problem statement before we start our solution, but very briefly, okay? Okay, so I would like to say a little bit about that problem, but I see that some of you are still writing, so I can wait like 1 minute or something. Yeah, no worries. Okay, so that problem, yesterday I had to like think what they actually want me to do, you know? And actually after solving it, I figured out what the problem was about, yeah? So I want to say something. I hope I'm not going to say too much, yeah? So anyway, what did I tell us? First of all, please look here. They told us that this is our feasibility region, yeah? Here, they said it here, yeah? So that means that our sphere can move in that blue area, yeah? It can, I don't know, it can start here, and it can, like, I don't know, start moving here, then go back, then again here, then back, and I don't know, maybe it can stop, maybe it can move again, yeah? Anyway, it cannot leave the feasibility region, yes? And by the way, that motion does not have to be that nice oscillator, yes? Like going back and forth, yeah? That sphere can do anything it wants in that feasibility region, yes? But it cannot leave it. Okay, that's first thing I realized yesterday. Second of all, they told us that we have an expression for acceleration here, yeah? And it's given to us explicitly, so it's already good, yeah? It's already fine. Okay, so we are happy about that. And they told us that our sphere starts from here, yeah? From lambda 4. They said that they can put that sphere anywhere. They can put it here, they can put it here, or they can put it here, and something will happen. Okay? However, they decided that they are going to put it here, and they are going to release it from rest with velocity 0. Okay? And they told us to find the range of motion. Yeah? So basically, they told us, so for example, that's what I was looking for. So for example, if they release it from here, our sphere will stay only in this region. It will just move here, for example. Okay? And they basically told us to find these bounds. Okay? So I call it S mean, yeah, S mean, and S max. S mean and S max. Okay, is it like clear what's going on in here? Yeah. Interesting problem, isn't it? Yeah. I just solved it yesterday and I was like, aha, that's what they're asking for. Okay. So what do we know, first of all? We know that our S in here is lambda divided by 4, velocity is 0, and also we can find that A is equal to 8. Let me show you that it is true, okay? So we can basically take our expression for A0 sine 2 pi divided by lambda, and instead of S, I'm just now putting here lambda divided by 4, yeah? Because this is where we are. So I believe that this will be basically A0 sine pi over 2, yeah? And this is 1, by the way, this is 1. So this is A0, and they told us that A0 is 8 meters per second square, yeah? Okay, so that's why A is 8, okay? And also what's important, that this is a positive number. So basically our A points this direction, yeah? It points to the right. So basically we know that our sphere is going to go that direction, okay? Not the other one, but it will start going that direction. Okay, with that information, we can start solution. Unless there are questions to the problem statement. No, solution, okay. Solution, okay. So I would like to start from integrating this expression, okay? A is equal to A0 sine 2 pi s divided by lambda. And please observe that our A is basically a function of position. So every time I see that our A is function of position, we could actually integrate A like that, yeah? dv dt. However, every time I see that A is a function of position, I think of using the other expression, yeah? I am thinking of this expression. I can take dv dt, yeah? And I can multiply it by 1, but expressed in a smart way. So ds in here and ds in here. Yeah, I believe Professor Sonny did it on the lecture, yes? Yeah, and this is velocity, by the way. So instead of dv dt, we can actually use v dv ds, okay? When acceleration is a function of s, basically, okay? So let's do that maybe. V dv ds, and this is equal to a0 sine 2 pi s divided by lambda. Okay, what's the next step? Everything with v on one side, everything else on the other side, yeah? everything with s on the other side. Okay, so this would be basically v dv, and this is equal to a0 sine 2 pi s divided by lambda ds. Let's integrate. Okay, if I remember correctly, our thing starts from 0, and it also starts from lambda 4, yeah? And we will end up with some velocity obtained at some position, yeah? These are the integration bounds. So if I remember correctly from school, that would be like 1/2 v squared, and this will be a0 times lambda pi over 2 negative cosine 2 pi s lambda. Integration bounds are from lambda 4 to s. Okay, let's plug in those integration bounds. A0 here, yeah, I forgot about 0. Yeah, I believe that this argument is pi over 2, yeah? And cosine of pi over 2 is, I believe, 0, yeah? So actually we can get rid of this. We don't need that. So our expression is 1/2 v squared minus a0 lambda 2 pi cosine 2 pi s lambda. Okay, we're done with the integration. So yesterday I asked myself what to do next. Yeah, what to do next, and this is what I observed. I noticed that thing on the left-hand side is always positive or 0. This is always larger or equal 0. Yeah. And now let's look at the left hand on the right-hand side. So we have a negative sign in here. Yeah. These dice are positive. So the only thing is this. So the only thing to have our expression making sense is our cosine being lower or equal 0. Do you see? Only then left-hand side is positive and right-hand side is positive or 0. Yeah. So we must have that requirement. Okay. So we must have basically cosine of 2 pi s divided by lambda. It must be lower or equal 0. Okay, let's draw cosine. So I think that cosine looks like that. I think that cosine looks like that. Like that. And it's periodical, yeah? It's a periodical function. Okay, so we have cosine x, let's say, in here, and this is x. So this will be pi over 2, 3 pi over 2, minus pi half, minus 3 pi half. Okay, so our cosine is negative here. Yeah? So basically we can write that our 2 pi s lambda must be lower or larger than bless you 3 by 2. Rude, he didn't say thank you. Sorry guys, let's go back. Yeah, 3 pi over 2 plus 2k pi, yeah, where k is an integer. Yeah, and we have to do the same in here. Pi over 2 plus 2k pi. Okay, so now let's multiply our thing by lambda 2 pi, and we will end up with following thing. Lambda plus lambda k lower equal, oh no, sorry, not lambda. Lambda divided by 4. Okay, so this is our expression for S. These are our bounds, by the way. We are getting closer to our solution. And I realized that that expression makes only sense when k is equal to 0 or k is equal to -1. I will tell you why in a second, okay? I will put a drawing there, okay? So for k equal to 0, we will have lambda divided by 4, s, and 3 lambda divided by 4, yeah? And in here we will have minus 3 lambda divided by 4, s, minus lambda 4, okay? So why did I observe yesterday that this makes sense? I'm gonna steal a drawing, okay, from what I prepared earlier. I'm gonna steal this one, and probably some of you already see what I'm talking about. Only these two regions or these two subregions lay in our feasibility region. So you guys can probably see that for k equal to 0, we will be here. Yeah, this is for k equal to 0. And we are basically we start from lambda divided by 4, and we are going to 3 lambda divided by 4. Okay, there's also another region here. Yeah, this is for k minus 1. It starts from minus 3 lambda 4, and it ends at minus lambda 4. Okay, we ended up with two regions. Which one is not physical for sure? The one on the left, yeah, obviously. This guy is not physical. Why? Because they told us that our motion starts here, yeah? Because we start at s equals to lambda divided by 4, yeah? So we cannot jump to the another region, yes? Yeah, we must stay in this region. And that guy is, by the way, physical. This guy is physical. This is okay. Physical solution. For two reasons. First of all, we start at s equals to lambda 4, lambda divided by 4, yeah? Which is one of the bounds of that region, yeah? And second thing is that we start moving to inside the region, yes? Because our vector A points to the right side, yes? For the second reason is that acceleration points to the right. Yeah. If they told us that acceleration points to the left at the beginning, that will be not physical solution as well. Yeah. But we know that we're gonna start at s equals to lambda divided by 4, and we are going to move inside the region. Yeah. That's why this is our solution. Okay. But let's put it mathematically. Okay. So they ask us to find S min and S max. Anybody want to tell me what they are? Don't be afraid. Yes. Okay, so this is our result. This is our answer. This is answer. And we're done with problem number 2, guys. Questions?
So everything makes sense, but how would you know to do all the electric
I know. That's why I prepared that before coming here. Yes, comes with experience. I hope you repeat that question to yourself. Okay, how do you know how to do things? Yeah, there is not a single recipe. For some problems we're gonna face this semester, there is a recipe. Okay, first do that, then do that, then do that. There are some problems like this one that it comes with experience. Okay, you must, sometimes see it, look at your piece of paper and say, aha, maybe I should try doing that. Maybe this will bring me somehow. Yes, that's why you have that thing inside your head. Yeah, you use it sometimes or all the time. Did I answer your question?
Yeah.
It was a tough question actually. I don't know the answer. Just comes with experience. Nice. Thank you. Yes. He was first. Sorry. Yeah. Oh, that's a good question. Yeah. So how do we know that it is integer? Or yeah, how do we know? Okay, that was exactly the same question in the previous discussion. Yeah. So look, our aim is to find where cosine is negative. Yeah. So basically, I draw cosine of x. Yeah. So basically, we figure out that cosine is negative between pi over 2 and 3 pi over 2. Yeah. However, it's not the only region where it's negative. It's also negative here. If I keep going, it will be negative here and here again. Yeah. It's a periodic. So this set is periodical. Yes. And the period of that set is 2 pi. Yeah. Subtract 2 pi from here, you will end up here. Subtract 2 pi from here, it will end up here. Yeah. So that set is 2 pi periodical. Yeah. So basically, and there's like infinitely many those sets. Yeah. So basically, I multiply 2 pi, our period, by k, which is integer, just to include all of those sets in our expression. Did I shed some light on the?
In the problem statement, it said that k was
Yeah. In the problem statement, they didn't say anything about k. Yeah. We come up with that together during our solution. Yeah. I hope I shed some light on the problem. Yeah. Digest on it. Yeah. And hit us up on the piazza or maybe office hours if you still don't get it. Yeah. Or something. Yeah. Thank you. Yeah. Thomas, you had a question?
I was just thinking, like, since the particle can move anywhere within the region, why can't it end up in the non-physical region? The answer is, I don't know, because we started talking about how it can go this way and this way and this way. When it goes this way, it would end up in the region that we said wasn't possible.
Yeah. So I think you should flip your thinking, because I think that you start thinking from the end. But they told, so there is an if statement here. Look, there's an if statement here. Okay, so they told us that we are going to put that sphere here, and we're going to release it from rest. Give me the bounds. Yeah, it will stay in. Oh. At home, solve it for example, I don't know, solve it for s equals to, I don't know, your favorite number, I don't know, s equals to lambda over 3 and velocity equals to -2. So these are initial conditions. Solve it at home for these initial conditions. You will end up with different s min and s max. Yeah. Maybe it oscillates. I don't know what the motion is. Yeah, but probably it oscillates. Do you see it?
Yeah.
Yeah, it's an if statement. Yeah. Yes, sir. Yes. Yes, because they gave us that our particle has to obey this expression. Yeah, this is our so-called equation of motion. We will talk about it later this semester. Okay, this is equation of motion. EOM, equation of motion. Okay. Yes.
Can I just say,
Yes, of course. This one?
Okay, yeah. I didn't understand why you had that. Okay, I misunderstood the whole like. I didn't understand why it was pi over 2 on the left and then pi over 2, but it's capable of taking the bounds when it's okay.
Pi over 2, pi over 2. 3 pi over 2, 3 pi over 2. Yeah. Yeah, by the way, this is my solution. I didn't check the solution that will be on Canvas today. Yeah, today there will be, yeah, you can compare my solution with the other one. Maybe they come up with an easier way to explain it. I like that way. Yeah, I think it's easy. Yeah. Yes, sir?
So the acceleration function has like an oscillating portion to it, the sign.
Yeah.
The velocity would have the cosine, and the position would have also some form of sign.
Yeah.
Would it be safe to assume that the particle will sort of oscillate?
It will oscillate actually, yes. I changed my mind.
I was trying to make sure because I'm like, I think it oscillates.
It oscillates, yes. It oscillates, yes. My bad. Yeah. Okay. There was a hand there. Yeah. Any other question? Yeah. How does it look like from your perspective? Is it like digestible? Yeah. Is it great? Okay. Just try to look at it one more time and hit us up with some questions. Okay. Should you have questions? What now? Example number 3. Do you want to do it? Let's do it. Okay. So please familiarize yourself with the problem statement before we start our solution. Oh, start listening to me. Okay. Yeah. Okay, this is our problem. Okay, so this is exactly the same problem as before. I mean, example number 1, yes? There's one difference. This time, we are going to express our motion in this coordinate system, yeah? A little bit tilted. It will be tilted, yeah? P and Q. And earlier, we just expressed the motion in that more civilized one, yeah? So X and Y, yeah? So not tilted, yeah? Okay, but the methodology can be exactly the same. So solution in the P direction, yes? In the P direction. And to be honest, this is my routine, yeah? So this is my recipe. Yeah, and what is your name, excuse me? AJ. AJ?
Yeah.
Okay, so this is one of the problems where there is a recipe, yeah? So I follow these steps, yeah? And I actually wrote down all of these equations yesterday. And after writing them down, I noticed that I don't need them to solve that problem, okay? So we're gonna skip that part, okay? Unless you really want me to write it down afterwards, yeah? Let's focus on what happens in the Q direction, okay? In the Q direction. In the Q direction, yeah. Because we just need equations from here to solve that problem, okay? So again, what do we have? Acceleration, yes? AQ is equal to minus G cosine theta, yeah? Before it was minus G because Q was aligned with Y. Now G is not aligned with Q. That's why we have to do some projections here. You all see that. I know that. And again, a very important thing is that this is constant. Yeah, so we don't have to integrate. If you want, you can, but we can also remember our expressions, yes? VQ is equal to VQ0 plus AQT. Let's fill it out. VQT is equal to, but I have to do those projections, yes? Let's do it here. I must project V on this direction, and I must project V on this direction. So I will have VP0 and VQ0. And I believe that VP0 will be V0 cosine beta, and VQ0, it will be V0 sine beta. Okay, so it's V0 sine beta minus G cosine theta t. Great. This is our expression for v of t. Okay, let's find y vq of t. Yeah. Now yq of t, it's yq0 plus vq0t plus 1/2 aq t squared. Okay, let's fill it out. This is 0, and we know everything else, yeah? So yq will be v0 sine beta t minus 1/2 g cosine theta t squared. Great. We're done with our routine. So now, guys, they ask us to find h max, yeah? So can one of you tell me how to use these two equations to find h max?
VQ being 0 because it's at max.
Thank you. That's the correct answer. So basically, our VQ at that point, this will be our VQ, yeah? Sorry, this will be our V actually, yeah? Yeah. V will be equal to VP basically at that point, yes? And VQ will be equal to 0. There's no VQ. So let's use that idea. So basically we know that VQ at H max is equal to 0, is 0. So 0 is equal to V0 sine beta minus G cosine theta T, I don't know, T star, T max. Let's go with T star, yeah, T star. Okay, and we know that T star, so time to reach that maximum position is basically V0 sine beta, G cosine theta. Great. And now, yeah, and now we're gonna plug that T star into other equation, yes? So basically, Y of T star is H max, yeah? So our H max is equal to V0 sine beta, V0 sine beta, G cosine theta. I know, guys, that you know how to do the rest. Yeah, I'm just gonna do it quickly, okay? Cosine theta, V0 sine beta, G cosine beta. Okay, let's simplify that. So we can have H max is equal to basically V0 squared sine squared beta, G cosine theta minus 1/2 of exactly the same thing, by the way. V0 squared sine squared beta, G cosine theta. G squared. So we basically have one thing in here minus half of exactly the same thing. So we will end up with this. And this is the end of the problem. This is our H max, exactly what they asked us for. So, well, thank you for today. Oh, wait a second. Questions, of course. Yes? I can, of course.
It looks like from the where you drew that blue line in the we have YQ of T, like at the bottom of the screen there, V0 sine beta T. When you brought it down and you set it equal to 0, are you missing a T there, or did that T go somewhere?
Here?
Yeah.
where exactly is the mistake.
So
This
like
line?
V0 sine beta, is there supposed to be a t followed by that?
No,
Or no.
no, this is expression for velocity, sir. So this expression is this expression. This expression you're asking for is this expression.
Oh, you run it from there. Okay, that's the velocity, correct?
That's velocity, correct. Yes. Yeah. Okay, guys, are there any other questions? If not, just make sure that you enjoy your weekend, okay? See ya.